so yeah, if you didn't turn it in already, make sure you turn in your SLP upload. I've got it open till I think 11:55 this morning, so 50 points out of 100. Make sure you turn that in. And there's a template you download from here. It's a PowerPoint, and just go ahead and edit it up, fill in the information, save it as a PDF, upload it. I only need one of these per group. If you uploaded more than one per group, I'll just print out the first one that I find. And I'll assign credit based on who's listed as being the team members, so make sure that that part is accurate. So make sure you do that. All right, any questions so far? So we were looking at processes in Bash last week, and I want to talk about processes from a programming perspective today and tomorrow. So how do processes come into existence? Bless you. So if we do this process display, right, PS, a lot of the latter processes, the ones owned by Nick, this is my laptop, right, you can track who owns what. Process 2110 is running something called K-Launcher, and that's owned by 2109. 2109 is KDE init5. That's the part of my desktop management system, and that's owned, that was created by parent process ID 1, right? UUIDD 1969, parent process of that is 1. A lot of processes are owned by this process 1. Process 1 is called init. It's the first process that's created when a Unix system boots. And think about the life of a CPU when you apply power to it, right? It's hardwired to fetch an instruction, decode it, execute it, fetch, decode, execute, right, over and over and over again. The instruction it's fetching is based on the program counter. It usually starts off at 0 or something predefined, and it's just fetch, decode, execute. Somehow we go from the CPU doing this fetch, decode, execute to the idea of an operating system where we have processes and tasks and things like that. There's a change in sort of the fundamental essence of the system. That change is basically what we refer to as bootstrapping, right? The CPU is always doing fetch, decode, execute, but somehow it starts off by doing very particular fetch, decode, executes that lead to all of this stuff, right? And it's a stepped process. We start by running some pre-programmed code. So go back to like a really old PC model, right? It starts executing the BIOS, so something that was on a physical, non-volatile memory. And that's used to eventually read in a bit of information from a hard drive, the boot sector, and start executing instructions in there, which are used to read in something much larger, which is sort of the startup of DOS, which is used to build up this whole multitasking system. And eventually we get to this stuff. So most of the stuff for Unix is written in C. Some of the low-level stuff gets written in assembly language, but most of it's written in C because you want to be able to just take this thing that is Unix and compile it for a new CPU, right? Something that maps C to ones and zeros differently. So you need to be able to, from a C program, create processes, right? Once you're up and running in a Unix environment. And so there's a function you can call in C named fork. And fork is used to create a new process. And it's really the way that all processes come into existence, other than maybe init, the first process. Processes are created by calling fork. A fork is an interesting function. You call fork, you don't pass it anything, it returns an integer. PIDT is basically an int. And let's just play with it. So I'm just going to make a two-line test program. I'm going to call fork. I'm going to save the return value in this integer called result. And I'm going to print out what that value was. Okay, simplest test program in the world you can imagine. And fork comes from, I don't think I need both of those. I'll put them both in anyway. All right, I can compile. There we go. All right, so let's see what fork does. Does something a little odd. It printed out, it did that print statement twice. And if I run it again, it prints the print statement twice, but that first number changes from 2424 to 2426 to 2429. So the code is pretty clear. Call fork, print out this one line. Right, but it's printing twice, which is a little peculiar. So what's going on? When you call fork, it creates an almost exact copy of the current process. It's an exact copy in that it has the same code as the current process. The place in the code where it is executing is exactly the same. The only difference is it has a different process ID, right? It's a new process. And the return from fork is different. So let's throw in some more diagnostics. So let's print out when we're ready to call fork, let's call fork, and then let's print out the result of fork. I'll get rid of my goodbye. So it says getting ready to call fork, it calls fork, and then it prints out the result twice. So when you call fork, your process gets cloned. And when fork returns, you now have two of your processes running. And they each set their copy of result equal to the return value from fork. And they each print out result of fork equals, and they print the value of that return value. And what you can see is that one of these processes, fork returned a big number, and the other one, fork returned a 0. So this is actually creating a new process that's running in addition to your current process. So let's do something different. Let's go ahead and call fork, print out the result of that call, and then let's just print out 200 consecutive integers side by side. And we'll throw a new line at the end just for fun. Alright, that's not terribly surprising. But this may be a little more surprising. So, getting ready to call fork, it called fork. Two processes running, each of them said what the result of fork was, and then one of them started printing out consecutive integers. And it made it through number 280. And then all of a sudden we went back to 1. Why? Because the other process got a slice of time and started printing out its values. And it printed out values up to 793. And then the first process got a slice of time and continued from 284. It had left off at 280. I don't know where 281, 2, 3 went. They're probably somewhere up in here. But it continued from 284 and printed out values up to 535, and then the second process started in at 796. So we have two processes running, and they're kind of doing their own thing independent of each other, right? Which is what we're seeing here. Yeah.
So they are completely independent.
They're completely separate processes now. And if we do this again, so it looks like the first process made it up to 1,654. It started to print 1,655, but after it printed that first 5, the second process woke up and said the result of fork equals 0, new line, and then we got the last digit of 1655, 1656. And the first process continued until it got up to 1859, and then it started to print 1860, but that 0 came from the second process, and it started printing out 0, 1, 2, 3, and so on. So they're completely independent. They're not even waiting for the other process to stop saying something before they start saying something themselves, right? They're two completely separate processes, and that's kind of cool. And if I do PS, I've just got my original bash process and my PS. So let's play with sleep. Sleep is a function I can call that will sleep for a specified number of seconds. So let's play with this. Let's get rid of our loop. And let's sleep for 120 seconds. And I'm going to run this in the background with an ampersand. So it's hanging out there. Let's do a ps-l. And I ran this by saying go, but you notice I have two go processes listed. The first one is process ID 2528. The second is process ID 2529. Okay, 2528, the first process called go. The parent of that is 2304. That's my bash shell. That's the process that was created when I said go. The second go process, 2529, the parent of that is 2528. That's that first go command. So in bash, I said go, that created this process. Inside there, it said fork, that created that process. And notice one of the returns from fork was 0, the other was 2529. That's the process ID of this new process. So after a few more seconds, our 120-second sleep will expire, and both of these processes will exit. So what's the general picture here? You have a process. It's got some PID. It's going along doing its thing. At some point, it says fork. Okay, it will continue doing its thing, and it also creates a second process which continues doing its thing. So this is called the parent. This process that's created is called the child process, or just the child. The original parent process that called fork, I is equal to the process ID of the child. The child process itself, I is equal to 0. So that's how you know if you're the original or the copy. You check the return value from fork. If it returns a 0, you're the copy. If it returns something other than 0, you're the parent, and the thing that it returned is the process ID of the child. Alright, so our process is finished. So we can do some things in here. Alright, so we can look at that return value from fork, which is called result. So if result is equal to 0, we know that we're the child process. Yeah?
And the program will never be assigned the ID of 0?
Correct. Yeah, 0 is reserved. So if the result from fork is 0, we can say I'm the child. Otherwise, we can say I'm the original process, and we can report the child ID, which is whatever the value of result is. And we can use that differentiation, am I the child or the original, to now start doing something different from what the other process is doing. If you want to have two processes that do something different, for example, one process is called a init, which is out there to create other processes. The other process is a web server that you want to run, Apache or something, right? So you can use the fact that your call to fork return to 0 to say I'm a new process, and you can go off and do something different. So we have an exuberant child process that says I'm the child, it'll sleep for 30 seconds. We'll go ahead and call sleep. And then it'll tell us that it's woken up. Alright, the original process is going to say I'm the original process. We'll do a little countdown timer. So we'll loop for 5 seconds. And then it's going to kill the child process. And then go to sleep. Alright, so the child process is simply going to go to sleep for 30 seconds and then tell us when it's awake. But the original process, the parent is going to wait for 5 seconds and then it's going to use the kill function and it's going to pass it result, which is the PID of the child. And that should kill the child process. And I need to include something else for kill. So I want to know how to use the kill function. If I just say man kill, it shows me kill parentheses 1 because there is a kill command available from the shell. I really want to know about the function kill that I can call, right? Which functions are in either chapter 2 or chapter 3 of the manual. So I'm going to say man to kill, and if there's a version of kill in chapter 2, it'll give me the documentation for that. And that tells me that I need these two includes. I just need signal.h. I'm going to kill with a 9. This is not my day for syntax. Okay. So let's run this in the background. And so we have our two processes out there. And then it says waiting 5 seconds, killing process 2647. And if I look now, 2647, it's still out there, but it's listed as defunct. It's been killed, but it's still associated with this other process that forked it. And so it shows up on PS. Defunct basically means the process is dead, but it hasn't been thoroughly cleaned up yet. When my main process exits finally, that defunct process will go away. And you can get into weird states with processes. This Z over here is a bit of a zombie thing. The process is dead, but it hasn't totally gone away yet. So when you hear about zombie processes, alright, so we got one zombie on our system now. And if we kill off the original process, the zombie goes away. So you get zombies, you can get orphans. If a parent process dies before the child becomes orphaned. So here the child's going to go to sleep for 30 seconds. If we're the parent, we're just going to return, right, which will kill the parent process. So the parent process has exited. The remaining child process called go, its process was 2669, but its parent process is now 1. 1 is the init process. So that adopts orphaned child processes basically, because every process needs to have a parent except init. And so if the parent process dies, it gets adopted basically. And that's what PBID points to. And then it woke up, and that's where it exits. Okay, is this making some sense? Well, let's do something simpler. Let's just make a one-line test program that just says fork returned and see what the value of fork is. All right, so that's what we started with. Let's do that 4 times. What's going to happen? Something different. So we got 16 lines of output here. Actually, we got closer to 32 lines of output here. So let's go to sleep at the end here instead of exiting. Let's run it in the background and do a PS. Here's what my system looks like right now. So I've got 16 processes named Go running. They all have a different process ID. And you can track the lineage through the parent IDs, but if you look at the source code, you can imagine what's happening here. We run our main process, that's a single process. And we say fork. So now we get a pair of processes, and then we execute the next instruction. So each of these threads executes a fork, so this one creates a child, and this one creates a child. And they each call fork. And so each of these creates a child. And then those all say fork, and so you get another branching off, and so you end up with 16 processes running. And they've probably exited by now. So we're back to where we should be. Okay, so this is what a fork bomb is. Fork bomb is a really simple thing to write. Right? That'll crash some systems. Because it will call fork repeatedly, and each time it calls fork, you get twice as many versions of this program running, which are each in the middle of this while loop, and so they each call fork, and each time it loops, it doubles the number of processes that have been created. We only have a finite number of processes you can run on your system before you run out of resources. And you either run out of process slots, which can be a bummer because to execute the kill instruction or the PS instruction, you need to create a process. And if you're out of process slots, and if this is constantly trying to fill up any available process slots, it's really hard to do anything to see what's going on in the system or to kill these things off. And so sometimes this just causes what's called a kernel panic and the system crashes. Now, don't try this on the Linux server, but the Linux server should be set up to only allow you a certain number of processes, and it'll refuse to create more than a certain amount. But I haven't like acid tested that, so don't do this because that's basically a denial of service attack. If I do this on my laptop, it will almost certainly crash my machine, so I'm not going to do that. But I mean, it's you know, it doesn't take any cleverness to do a denial of service on an open system like Unix. So forks can be a little tricky to experiment with, right? If you're not trying to be malicious, but you're trying to play around with process creation and so on, you can accidentally do something like this. And unlike other cases where an infinite loop, you just control C out, right? Sometimes that doesn't work. But they're fun to play with anyway. All right, so if we don't want to go all hardcore, but we still want to be able to create new processes from inside C, there's easier ways to do this. So one is the function system. So system is a callable routine. You basically pass it a string, and it executes that string as if you had typed it in at the command line. I'm just going to keep making libraries that I include here. So let's just execute a call to system with the string date inside. And if I do that, it prints out the date. And if I call system and I put in, say, an output redirection with a greater than sign, right, that works fine. And in this case, it creates a new file that contains the date at the time that I ran it. So there's a system call that asks to execute the ls command and pipe that into word count, which gives me 3 fields of output, number of lines, number of words, and number of characters. Then I pipe that into awk with a program that says print field 1, which should just print the number of lines. So this should tell me how many files I have in my current directory. All right, so I got 92 files. And yeah, that's believable. If I just do ls pipe into word count, there's my 92. So system is pretty powerful. You can still get yourself in trouble. Right, there's another fork bomb basically. Because this program is called Go, and so when this runs, it's going to create a new program called Go. This program will exit right after that. So it'll create a process and die, create a process and die. But I've got a feeling it'll still end up chewing up my resources. Now, if I put that in a while loop that runs forever, that's totally just going to fill up all my process slots. But if you just want to be able to execute some command on your Linux system, right, from a C program, system is a really easy way to do that. and system just executes and then it comes back to your program and continues running. So I can print something before and after the call to system. But it does something interesting sometimes. Remember, when you do output, it's what we call buffered output. Some of you have stumbled across this in debugging code. Just because you say printf blah doesn't mean that blah immediately appears on your screen. Okay, when you say printf blah, blah goes into an output holding area. That output holding area does not get copied to your screen automatically. It will get copied when it gets so full, when you've outputted so much stuff that it can't hold anything else in this holding area, it dumps it to your screen. It'll also copy it to your screen when you type out a new line. So when you do a \n, what you've buffered up gets written out. Here I said print out number of files : but I didn't put a new line. So that was waiting in the output area. And then I called the system command, and the system command ran, and it printed out 92. And then I said print out goodbye with a new line that got tacked down to the holding area. The new line said force that out, and so it printed out number of files goodbye. Like that. So if I force a new line here, right, then it does what you're expecting. But I didn't really want a new line. I wanted the 92 to come out at the end of that line that says number of files. So there's another call that we can make to a function called fflush. Fflush is used to flush an output stream, to take that stuff in the holding area and force it to go out to the actual output device. So if I say fflush standard out, that should have the same effect as writing a new line. Alright, so there's a number of files that got forced out to the actual display, and then the call to system ran, and that printed out a 92. And then it said goodbye. So that's just a nice thing to know. Alright, so system will let us execute commands. It lets us continue running our program after we execute the commands. The big disadvantage of system is we have no way to interact with the command once it's running. It basically launches it and it goes off and it does its thing. And if it's a command that needs to get some sort of input, we have no way to supply input to it. So for example, BC is a command that does calculations. BC, we can say 23 times 7, and it gives us 161. It could be nice to have access to that from inside a C program, right? Because BC will also let us do ridiculously large calculations, right? Which regular C won't let us do. But system doesn't give us a way to send stuff to it or to capture the output from it. The result of the system command comes up on standard out. We can send it into a file and then open up the file and read that, but that's kind of a pain. So we don't have an easy way to capture the output. We don't have any way to specify input. So if we want to interact with a process, including manipulating input and output, we need to do some more work. So we need to talk about exec. And I'm going to talk about execl, but there are a variety of versions of exec. Execl, execl-p, execl-e, execv, execv-p, execv-pe. And they all basically do the same thing, but they have different arguments that you pass to them. And execl is probably the simplest in terms of arguments. It's a family of functions. That sounds pleasant. somewhere in here they give you the punchline. I don't know where in here, but I'll give you the punchline. Execl, you basically pass it the name of an executable program, and it will replace itself with that executable program. It's not creating a new process. What it's doing is basically changing its essence to be the essence of some other program. It's like remapping your DNA, right? You still have the same driver's license, you have the same name, but you become a different entity. It's basically what the exec functions do. And under return value, it makes this interesting statement: the exec function returns only if an error has occurred. Because here's what's going to happen. We've got a main program. It's going to be running along doing some stuff. It's going to call this exec function. At this point, the code that makes up this process changes from this compiled code to whatever compiled code corresponds to the program name that we put in here. And so if we have, a print statement down here, that print statement never gets a chance to execute. Because after exec is called, in the middle of that call, all of this changes and becomes basically the code for whatever function we specified inside exec. Alright, so I'm going to put in the print statement here, so we're ready to call execl. Put in the statement when we're done, and then let's call this function in the middle. So where's date? Date is under bin date. Okay. So I'm going to call /bin/date. Okay, that's a file, it's an executable. This function is going to open that up, it's going to read in all of those ones and zeros in there, the gobbledygook, right? It's going to read all that stuff in, and it's going to use it to overwrite its own memory with the code from that program. And execl needs a second argument. We can just pass null. It has to do with passing variables to that environment. We'll just use null. And so there's our 3-line test program. Okay, maybe it's got to be trickier than that. Yeah, close enough. Let's just go for it. Oh, no, can't just go for it. Okay. All right, so what does it actually want here? Constant char star arg. Alright, I'm playing without a safety net. Let me try a few things. Nope, it's not going to like that. Okay. All right, so forget a few of the things that I just said. Let's play with execv. So this is a newer system than last year when I did this. So execv, same thing. The first argument is the path to the program that you want to execute. The second one is an argv array. Okay, and I'm just going to pass it the argv array that main was called with, just so it has something that looks like a car star star. I don't actually care what that value is. So, so I'm going to call execv instead of execl, and I'm asking it to execute bin date. Okay, so the punchline is going to say ready to call execv. It's going to call execv and then say done calling. And it says ready to call. It executes the date command. It never comes back and says done calling, right? Why? Because that print statement after the execv call never gets executed. Because once execv is called, the code of go 0 is replaced with all of this, right? The code from the date command. And this can get you into some strange things, like if I exec bin bash. Right, well, what happened? Well, I started a new bash shell. Right, and if I do my PS, I have two bash processes sitting out there right now. And this second bash process was created by the first process. Its parent ID is 2304. So I can exit this and I'm back to my original process. So let's just throw a sleep in the beginning. Let's run go 0 in the background. Let's do our ps-l. So we've got bash running. That's process ID 2304. It created a process called go 0. That's what I typed in when I said go 0, which was 21,336. And now if I do a ps-l, 21,336 is now running the command bash. Right? It's the same process ID as go 0, but it's running something totally different now. So the process doesn't get destroyed, it doesn't create a new process, it simply changes itself. Okay, and this is how processes get created. It's a combination of fork and exec. You call fork to make a new process, which looks like the original, and then that new process calls exec to change its identity into whatever you want the process to be doing. Alright, so every time you run a command, that's what's happening. Bash is creating a new process and then changing it into process that runs your command. All right, so we'll play around with putting those together tomorrow, and then we'll start talking about how we communicate with these new processes. So how can we send things to the input of a created process or read its output? And so we'll start talking about the pipe command from a C program, and it works like a pipe, vertical bar pipe in Unix, where we can actually create pipes and manipulate them from inside C code. So we'll play around with that tomorrow.